Hi, my name is Elgin Lam. I'm a senior prototyping engineer here at Amazon Web Services. I help our customers build prototypes to demonstrate the art of the possible and accelerate their digital innovation journeys. In this session, we are going to talk about the importance of data captured at the edge and talk through various use cases in the aerospace industry. We'll also have a demo of AWS IoT TwinMaker, our new digital twin service launched at reInvent 2021. One of the greatest achievements in the 20th century was for mankind to step foot on the moon. Apollo 11, the first manned spaceflight on the moon, sparked a series of moon exploration missions by the National Aeronautics and Space Administration, or NASA. On April 11, 1970, Apollo 13, carrying astronauts Lovell, Hayes, and Swigert, departed Earth for a 10-day mission to perform scientific experiments on the moon. Back on Earth, NASA's Mission Control Center had flight controllers measuring telemetry, all the way from lunar module performance to the heart rates of the astronauts. In the 56th hour of the mission, while the oxygen tanks were being stirred, there was a large explosion. One of the oxygen tanks had damaged insulation, which caused it to blow. The ensuing conversation gave us the popular catchphrase, "Houston, we have a problem." The astronauts had to abandon their landing of the moon and use the moon's gravity to slingshot them back to Earth. Telemetry was critical in helping astronauts understand their options and have mission control back on Earth understand the problems and offer solutions. There were two major hurdles that the astronauts had to cross: carbon dioxide buildup and re-entry procedures due to lack of power. In the first concept of a digital twin, Mission Control back on Earth recreated the carbon dioxide scrubbers and the re-entry procedures using physical twins. 5 days after the incident, the astronauts successfully entered the Earth's atmosphere safely. Telemetry is the collection of measurements and data in near real time. This data provides value in a multitude of industries and use cases. As already stated, telemetry is used in space exploration. It's also used in the motor racing industry to get insights into the performance of various components of cars: tire heat, pressure, G-forces, centers of gravity, and suspension travel. Each car has around 120 sensors, each generating 10 megabytes of data per second. Capturing these insights can allow for tweaking of the car, where even minute changes can have significant impact on track performance. Aviation is another use case where telemetry is used. Airports all over the world track aircraft flying in the airspace with data like airspeed, altitude, heading to help air traffic controllers maintain safe separation of aircraft. With a combination of telemetry and IoT technologies, we can now have near real-time visualization of aircraft. This capability allows for faster diagnosis of faults, allowing pilots to concentrate on the challenging task of keeping the plane flying. Digital twins can provide a real-time counterpart to the physical aircraft. The digital twin can react in the same way as a physical asset, as well as providing telemetry data on specific parts as needed. Capturing this data allows for predictive maintenance and anomaly detection to be done based on the telemetry and visualization of digital twins. In April 2010, an aircraft flying from Surabaya in Indonesia to Hong Kong started to experience engine pressure fluctuations during its climb to 39,000 feet. Despite consulting with the maintenance crew on the ground, they kept flying as the issue wasn't deemed critical. Towards the end of the flight, one engine started to stall and the other was stuck at 75% maximum thrust. Even though the aircraft managed to land, it blew out its tires and scraped an engine. The cause was later deemed to be contamination of the fuel. During emergencies like this, having sufficient telemetry reported back in real time can help ground staff and aircraft manufacturers make the right decisions and advise the pilots accordingly. Visualization of an engine digital twin could have helped engineers determine the fault remotely and provide advice to the pilots who were busy trying to keep the aircraft flying. I'm now going to run you through a scenario of how telemetry, IoT, and visualization can work together in an aviation setting. We'll be flying a commercial aircraft in a flight simulator, sending telemetry to AWS IoT Sitewise, and viewing the data in a Grafana dashboard and AWS IoT TwinMaker. We'll take off in an Airbus A320 from the airport's runway, then ascend to 3,000 feet, where I'll shut down the engines to simulate a bird strike. This is a scenario similar to that of US Airways Flight 1549, which had to ditch in the Hudson River after a bird strike disabled the aircraft's engines. We're currently in an Airbus A320 taking off from Singapore Changi Airport. Today's flight will be from Singapore to Bangkok, bringing us over Malaysia and the South China Sea. The Airbus A320 is a twin-engine commercial airliner that is flown by a large number of airlines around the world. We have a companion application running on this machine. This application might be running on AWS IoT Greengrass in a rail aircraft in order to communicate with AWS IoT Sitewise. You'll be able to see the telemetry being uploaded in real time to AWS IoT. As you can see, the data that's being uploaded includes our current location coordinates, speed, altitude, pitch and bank angles, and the amount of fuel we have remaining. We're currently lined up on runway 02 left. Before we take off, I'd like to run through the scenario that we will be simulating. After takeoff, I'll show you the metrics flowing through to IoT Sitewise and the TwinMaker console in Amazon Managed Grafana. We've set up an asset in IoT Sitewise that reflects this specific aircraft. As you can see, this is the tail registration number that matches the one on our aircraft today. The measurements that are being captured are reflected here, and the MQTT notification topics that these measurements are publishing to are also shown. These notification topics allow you to ingest real-time data to other MQTT endpoints like IoT Core. This IoT Sitewise Dashboard will allow us to view the data coming in real time. Since we are still stationary on the runway, our metrics are still pretty flat and not moving at the moment. This is the dashboard we've set up in Amazon Managed Grafana. Apart from metrics like engine RPM or revolutions per minute, we are also showing the flight path based on the coordinates that the aircraft is reporting. We also have a digital twin of the aircraft set up on AWS IoT TwinMaker, which will actually show an alarm when the revolutions per minute of the engines drop below a threshold. These two engines have turbines that rotate to generate power, and measuring the revolutions per minute gives us a gauge of how much output the engine is giving out. After takeoff, I'll be turning off the engines to show you an alarm that is set up to activate if the altitude of the aircraft is above ground and the revolutions per minute falls below a specified threshold. Even though we are on idle, you can still see that the engine turbines are running, and you can see this being reported in our AWS IoT Sitewise. The cockpit of the aircraft looks intimidating. It has a complex array of switches dials and knobs. Don't worry, we won't be requiring everything today, but I do want to draw your attention to these two switches behind the throttle quadrant. These two switches are the engine master arm switches. Post takeoff, I will return to this view and flip the switches to the off position in order to shut down the engines and simulate a bird strike. Let's take off now. As we begin to spool up the engines, I will show you the IoT Sitewise Dashboard where the dashboard is updating in real time. We now retract the landing gear, and you can see that the altitude data is being reported to IoT Sitewise, reducing the throttle to 70% for a steady climb. Before I turn off the engines, I'd like to show you the AWS IoT TwinMaker scene for this demo. In real life, you can visualize different points of data per model and model different models together. For example, instead of just one aircraft, you could be visualizing multiple aircraft and their relative distances to each other. We've set up an AWS IoT workspace and imported our 3D model into the resource library. The entity definition for the aircraft has also been set up, along with the components that allow us to connect to AWS IoT Sitewise and pull in the appropriate properties as needed. For further information on how to set up your projects, read the IoT TwinMaker guide available on the AWS website. I'll now be shutting down both engines to simulate a bird strike. When the engines are shut off, you'll be able to see the data in AWS IoT, register the changes and revolutions per minute. This time I'll be showing you the data from the Amazon Managed Grafana dashboard. As mentioned earlier, the two switches that we want to concentrate on are the two just behind the throttle quadrant. We'll be flicking them off now. These are the engine master arm switches. Now going back to our Managed Grafana dashboard, we can see that the engine RPMs are starting to drop, and they're falling below the 10% threshold, which is what we set as the alarm threshold. In the digital twin, we've also set up thresholds for our warnings, which are actually telling us now that the engine revolutions per minute are in an alarm state. what I want to do now is then to restart the engines, and we can be on our way. It does take a while for engines to restart, as this is a large airliner, and engines do take a while to spool up again. Here's the architecture for this demo. A connector, which is responsible for capturing telemetry from the simulator, sends the data to AWS Sitewise. AWS IoT Sitewise then sends the data to AWS IoT TwinMaker. We visualize the output from AWS IoT TwinMaker in Managed Grafana. Amazon Managed Grafana is a fully managed service for open source Grafana developed in collaboration with Grafana Labs. Grafana is a popular open source analytics platform that enables you to query, visualize, and alert on and understand metrics no matter where they are stored. AWS IoT Sitewise can also send data to AWS IoT Core. From IoT Core, data can be sent to other services. We are sending the data to Amazon Kinesis Firehose, which saves the data to Amazon S3 for logging. Having the telemetry data in S3 can aid in post-flight analysis and adding context to cockpit black box recordings. To import your 3D model into IoT TwinMaker, the model must be in a format compatible with WebGL. To convert existing Step 3D models to the GLTF format, you can follow instructions that are available on the official AWS IoT blog. You'll be able to see the link to the blog post later on. The cloud, IoT, and AI/ML technologies are transforming the art of the possible within industries. Customers across a range of industries from manufacturing, energy, utilities, to smart buildings are looking to digital twins to help them achieve business outcomes, such as improving their operations, optimizing the use of resources, and anticipating issues earlier before they become more costly to resolve. Digital twins have come a long way from the physical twins powered by a paper checklist on Apollo 13. Moving data from a physical system to a digital twin is used to power business outcomes, whether it is fault detection, preventative maintenance, or monitoring equipment in hazardous environments. We hope that you have enjoyed this demo. We encourage you to try to use AWS IoT services to achieve your business outcomes. AWS IoT TwinMaker is currently in preview and is free to use. As mentioned earlier, here is also a link to the blog post which explains how you can convert CAD files to the GLTF format. There are also code samples on the AWS Samples GitHub repository that you can use to kickstart your own IoT projects. I hope that you have enjoyed this session. Thank you for your attention.